This next section talks about setting up and calibrating the DCO. The DCO is a very important clock in the Msp430 as most of us use it for the main CPU clock. In the last section we talked about how the DCO was calibrated and it was done differently on some of the different Msp430 generations. Before we get into the details of calibration, let's just look at how the DCO works first. As we know, the digitally controlled oscillator, or DCO, generates a clock frequency. The way the DCO works, in this example we're looking at the F5529, is it can generate frequencies in one of 8 different ranges. So once you figured out which frequency you want to run at, pick a range that frequency falls into, and you can select that by setting the proper value in the DCO range selection bit field of the UCS control register 1. In reality, we don't have to worry about these bit fields specifically because driver library will handle that for us. In this example, we wanted to have a 1 MHz DCO clock. So we happened to choose range 1 because the 1 MHz frequency happened to fall inside of that. That means 1 will go in the DCO range select bit field. Picking the range, though, just gets us into the range. What we really want to do is pick a frequency within that range. As you can see here, the DCO bit field allows us to pick any one of 32 specific frequencies within that given DCO range. In our case, a DCO value of 18 got us the closest to 1 MHz. What happens though if the frequency we're interested happens to fall between two different DCO values? So maybe between DCO set equal to 18 and DCO set equal to 19. The digitally controlled oscillator has a modulation feature that lets us get frequencies in between the DCO and DCO plus 1. The modulator actually does this by modulating between those two frequencies to get an effective or an average frequency closest to the one you want. This does give us the advantage of actually spreading the clock energy between a couple of different frequencies, which reduces EMI, although it can generate a little bit of jitter as well. If you don't like this feature, you don't have to use it. You can turn it off, but it does let us get a little bit more accurate in our frequencies. Here's another way to look at the DCO modulation. You can see the two frequencies on the left that are feeding into the modulator, and the modulator then selects one frequency to the other to create an average DCO clock closer to the frequency of interest. Here's a summary of how the DCO works. 3 things we need to do. 1, select which range we want to use for our frequency. Then select a frequency tap within that range, and then finally pick a modulation scheme, one of the modulation schemes provided, to give us the frequency that we want in between the tap and the next higher tap. If all that seems a little complicated, just rest assured we have a driver library function that takes care of all this for us. All we really have to do is specify the frequency we want. It's pretty nice. With regards to calibration, let's start by looking at the G2553 and then the FR5969 devices. They're both calibrated at the factory. As we stated earlier in the chapter, for the G2553, the factory provides DCO calibration constants. That means for the frequency shown here, which we clipped from the datasheet, TI has already figured out the values for range, DCO, and mod. All you need to do is copy these values from the info memory into the clock control registers. To make it easy, they've created register symbols for these addresses. The FR5969 DCO works a little bit differently. Here, they've defined 10 different frequencies. So once you've selected the frequency you're interested in, just pick the value for DCO range select and DCO frequency select that match the frequency you're interested in. Just plug those values into the driver lib function and you're all ready to go. So we've just seen how factory calibration works. Basically, it's static. You set it and forget it. Let's move on to runtime calibration. In this case, it's not static. It's actually something done at runtime in the hardware. The 4th, 5th, and 6th generation families, F4XX, F5XX, and F6XX, provide this runtime calibration in hardware. Before we look at the hardware on the later devices, if you go back to the very first generations of the Msp430, they really had you do DCO calibration in software. You can see there's just a little kind of pseudocode up at the top, and it's basically just comparing your high frequency clock, DCO, to a known stable external clock, say a 32 kilohertz crystal. The nice thing in this, and doing this calibration, is we were able to minimize drift due to changes in voltage and temperature and so on. Unfortunately, it wasted time and, maybe more importantly, energy having to run the code to do this calibration. That's why the later devices, the F4XX, 5XX, and 6XX devices, have the frequency lock loop. It actually does this for us in hardware. So let's look at the frequency lock loop hardware, such as we find on the F5529. You can see there up at the top, the DCO and modulator circuitry works as we've talked about a little bit earlier in this chapter. It produces a signal called DCO clock. A bit field called FLL divide, or FLLD, gives us a divide down value from DCO clock. In fact, you can actually pick either one of these clocks as a clock source, DCO clock or DCO clock divide. Not only can you use DCO clock divide as a clock source frequency, it's also fed back into the integrator of the FLL circuitry. You can see that there's another FLLN divider value along the way. The FLL hardware, basically an integrator, compares the DCO clock, which has been divided down, against the FLL reference clock. That's either one of the external crystals or the internal reference oscillator. Based on the comparison of the divided down DCO clock and the FLL reference clock, the FLL hardware actually modifies the DCO and mod bit fields. In other words, we're controlling the DCO output through a feedback loop judged against the FLL reference clock. Finally, here's an equation that describes how the FLL hardware works. You can calculate the output for DCO clock by plugging in the FLL reference clock and the various divide values that are all bit fields in the UCS control registers. But do you really want to have to calculate that by hand? Wouldn't it be nice if there was a function that would do that for you? Let's turn to the next slide and look at the driverlib function that helps us out with that. Here's an example of setting the F5529's DCO with the Msp430 WordDriver library. Here we've written a function to set up mclock and smclock from DCO using the FLL. First thing we have to do is actually set up the FLL reference clock. You can see that right there. UCS clock signal init. We're going to set up the FLL reference clock. We're going to set it, in this case I guess we're using the internal ref-O, or reference oscillator clock, with a divider of 1. You might remember from the diagram that we looked at just previously, that reference clock was basically our time base. It was what we judged our feedback loop against. So with that set, then all we have to do is call the UCS init FLL settle function. This function does it all for us. We tell it what frequency we want to run at, so that's our mclock frequency in kilohertz. Then we tell it what the ratio is between the frequency we want to run at and what we've set our FLL reference frequency at. So those two clock values, the clock value we want to run at and the ratio between that and the reference clock frequency, it takes care of everything for us. To summarize, UCS init FLL settle does a few things for us. Given the frequency we want to run at and the ratio between that and our reference frequency, it does all the calculations needed to settle all the bit fields. It handles DCO mod, DCO range select, FLLD, and FLLN. So it calculates all of that for us. That's pretty cool in itself. Once the FLL is programmed, running, and settled, it actually also does the clock signal init for mclock and smclock. So it does a lot of different things for us. There is a version of the FLL function, just called UCS init FLL, that doesn't have the word settle in it. That means it doesn't wait for the FLL to reach a steady state. The FLL settle adds a little extra time to make sure that the clock, the DCO clock, settles into its frequency before leaving that function. One more short item before we leave the topic of calibration. You can also calibrate VLO. If you want to get a better handling on the timing of VLO, there's an app note that talks about using the DCO to calibrate or calculate the speed of VLO.